In the last video, we took a look at this interesting theorem that talked about how we could actually integrate functions that have certain symmetries. That is, if I had functions that were even or odd, functions that were symmetric across the y-axis or symmetric across the origin. Now, we're going to see here in this video and the next one how I can put this to use in some different examples. So let's take a look here at example number 4. Now, a good tip right off the bat to be aware of is that I know that the theorem up above will potentially kick in if I'm integrating a function from a negative of some value to a positive of the same value. Like here, I'm integrating from -2 to 2. This doesn't mean that I have to use symmetry, but it's a good kind of, alarm bell now should be able to go off that says at least thinking about symmetry is an option. So before I even start to consider symmetry, I know that no matter what route I take here, I'm going to need to make sure that my function is continuous in order to be able to integrate this. So I'll say that we see that f of x, which is equal to x to the 6 plus 1, is definitely going to be continuous on the interval from -2 to 2. It's a nice polynomial. And so we can use the fundamental theorem of calculus part 2. Great. Well, now I'm going to show really quickly here that even though it's possible for me to just immediately find the antiderivative here, that would be super easy. 1/7 x to the 7 plus x, right? Boom, I immediately evaluate from 0 to 2. I could instead, it's an option, check to see if my function is even or odd. So I'll start by saying this. We calculate that f of -x is going to be equal to, and I'll see what this looks like when I take -x and I plug it inside of my function. Now again, this is how I check to see whether a function is even or odd, or maybe neither of the two. I can go ahead and see here that if I take a negative times an x and raise it to the 6th power, I'm just going to get positive x to the 5th plus 1. And so this spits back the original function. F of -x is the same as f of x. And so f of x is an even function. Okay, it's an even function. So what I know is the following. I could then say that the integral from -2 to 2 of x to the 6th plus 1 times dx is equal to doubling the integral from 0 to 2 of x to the 6th plus 1. Okay, great. So let's try to evaluate this integral here. I'm going to have this 2 left in the front, but I'm going to have to think about my antiderivative. Should be again 1/7 x to the 7 plus x, and I evaluate from 0 to 2. All right, so this is going to be 2 times 1/7 times 2 to the 7th power plus 2 minus 1/7 times 0 to the 7th power plus 0. So this is what I have. Overall, I can see that ultimately this is just going to turn into a really big value. This is going to be 2 times 128 over 7 plus 2, or I could write that as 256 over 7 plus 4. And if you wanted to, you could combine those up into a single fraction, which I think would be 284 over 7. Okay, great. I found a final answer. And if you're anything like me, that answer feels really stupid. Well, maybe not the answer, but maybe the work to get to that answer. Because why in the world did we do all this work with even functions here? Didn't this just feel like a giant waste of time? I mean, couldn't we again have just skipped all 3 of these opening lines, immediately calculated the antiderivative, and just gotten to an answer? We didn't really even save that much time by making ourselves aware of the fact that f here was an even function. I mean, in fact, we probably wasted time. So in general, working with even functions is not necessarily always going to be a great time saver. It's sometimes going to be used for certain functions to make some things easier, but it's not often going to be used. However, when evaluating integrals with odd functions, things become very, very useful. And we'll see an example of that in the next video.